Alright, this is an introduction for the second lab, investigating constant acceleration. And one great case of constant acceleration that we have in the physical world is the influence of gravity, at least while we're close to the surface of the Earth. So what I want you to do is go ahead and make a prediction, and I want you to sketch what you think the position, velocity, and acceleration graphs would look like for a ball that is tossed straight up and then it goes straight down. Please do describe in words what these graphs mean. I am looking for text on the page when I say things like explain and describe. What I then want you to do is, if possible, go ahead and go to this website and download this Java file. I know that this will not work on a Mac or a phone, so I just put a screenshot of what these look like below. I'm not going to go down there because I don't want to influence your prediction. But what I want you to kind of do is think about why the graphs look the way that they do. And so while you're thinking about that, I'm going to go ahead and write the equations of motion. So we have position is initial position plus the initial velocity times time plus 1/2 acceleration time squared. And we also know that the velocity is the initial velocity plus acceleration times time. So take a look at these equations, and hopefully they'll help you explain why the motion graph is parabolic and also upside down if you think about if this guy is positive or negative, and why is this guy straight and also has a downward or negative slope. I'm going to jump forward just a little bit in the simulation here, so bear with me for just a second. Alright, we are past the point where I don't want you peeking. Now I have you calculate the slope of the velocity versus time graph. Pretty straightforward. Something that you know is that the slope is going to be the rise over the run. So we're taking a look at the change in velocity over the change in time. That is the slope of this guy. And think about if it has any physical meanings, and please remember to include units. Then I have you reset the simulation, and then I have you launch a projectile from some height. And again, I just put a screenshot of the simulation running on my computer if you were not able to run it. So this is what the graphs were going to look like for the second part. I don't have you make a prediction, so I can show you these. And then I just have you label a couple of things, and you can label it however you want to. You can use double arrows, A, B, C, 1, 2, 3, X's, draw lines, be creative, but label some various things. And to determine the position, velocity, and acceleration just at some specific points, like when it's at the top of its motion and fun things like that. I have you identify the acceleration and velocity just at a couple of important points. I again have you calculate the slope of the velocity versus time graph, and in case you aren't familiar with it at this point, yes, it does have physical significance. Tell me what that is. Then I have you use the equations of motion to figure out the maximum height, and it should match with the simulation. The simulation is perfect. And then I just have you do a calculation of how fast a projectile would need to be fired from the ground to achieve the same height. So that's just a little bit of practice using those equations of motion. Something to keep in mind is whenever we're looking for maximum height, what we're kind of saying is we're saying that's when the speed at the top is equal to 0.